Good evening, good evening, good evening. How is everyone on this fine evening? I know you're doing wonderfully because if you are staying, you have seen Tyler work. So I know you're doing great. Cold? Oh no, not cold. Frozen. Emily has gone past cold. Emily is just frozen to the bone. Excellent. Hi, guys. All right. So tonight we're really going to cover electrons. So this is covering a lot of information from chapters 1, 2, and 3 in your general chemistry review book. So if you've got that under your belt, wonderful. If not, hold on for the ride. This is going to be a lot of fun. All right. So we have other teachers in the room. You've seen Kyle, you've seen Paul, you will probably also see Sergey. Everyone, please make sure if you have questions, ask those in the Q&A. Okay, Paul and Kyle are ready to answer those questions, very excited about answering those questions. And if I don't answer a question that shows up in chat, I'm not ignoring you. We have a pace that we need to set. So if I don't answer a question that shows up in chat, Paul and Kyle will get that question as well. All right, let's have some fun and let's get going into our electrons session. So in this episode, we've got 4 different goals that we are going to set out to do. Our first goal is to really look at quantum mechanical model. So really get some of that quantum under our belts. Then we're going to recognize and use the periodic table, so we really need to understand the periodic table. Do we have to memorize the periodic table? What do you guys think? Yeah, not at all. Not at all. We've got that nice exhibit button. The AMC loves us, so we don't have to memorize it. We just need to know how it works. Then we're going to really look at how electrons are being shared with our intramolecular and intermolecular bonding. And finally, we're going to predict hybridization and bond angles in our molecular bonding. All right, our first thing that we're going to do is we're really going to understand the quantum model of an atom. So this is not something that's surprising to us. We know that the nucleus is going to be positively charged. This contains our protons. This contains our neutrons. Excellent. We've got that. Then we know it. We've got those electrons around it. Now, why are those electrons held in there? Why are they held in? Why don't they just go flying away? It's magic. Absolutely, David. It is the magic of electrostatic attraction. Yeah, attracted, so those opposite charges attract. This is the magic of physics. Absolutely. So when we have this, remember that these guys are always rotating around that nucleus. All right, let's get into the different things that we have to know. We're going to start with principal quantum number. Principal quantum number, or N, tells us what about where our electron is? What information does that give us? Yes, this gives us our energy level. This gives us our shell. Perfect. Kemi, we're going to get to the orbit in just a minute, which orbital it's in. So right now we're going to talk big, and we're going to talk about that shell. So the bigger the number, the larger the shell, the farther we are from that nucleus. And as we get farther out, our radius gets larger. This makes logical sense, especially when we're sitting here and we're looking at this. What is the max number of electrons that I can have in any given shell? There's actually going to be an equation for this. And yes, Rogelio, did I pronounce that right? You've got that. It's 2n squared. So when we look at this, 2n squared. Now, when we talk about the second shell, n equals 2, we definitely have 8 electrons. That is our max number. But what is our maximum number for our n equals 3 shell? Do that math for me really, really quickly. Yes, 18. 18. So remember, This includes, if we are above the first n, this includes s and p orbitals. If we're even higher up, it can include s, p, and d orbitals. So the maximum number, when you guys are thinking 8, you're thinking the rules that we have for the octet. All right, so remember 2n squared. Azimuthal number, that's our next one. What is our azimuthal number? Thank goodness this isn't a spelling test. So what does our azimuthal, or L, tell us about our electrons? This is our subshell. Good, Raquel. We're almost to orbital, guys. We're working our way in from big to small. So this is our subshell. And label for us, or name for us, because Paul really wants to know, what are our 4 subshells that we have? S, P, D, and F, dead on. You guys got it. So these are our possible shells, our possible subshells. Now, this goes from 0 to negative, or n minus 1, which is n is our energy level. So if we start with n is equal to 1, we get 0. If we start with n equals 2, we can go up to 1. So here's what you need to know about our azimuthal number here, our momentum, is S is 0, P is 1, D is 2, F is 3. It's going to come into importance in one of the questions that we're going to see in just a little bit. Now, in the periodic table, n equals 1 is that first row. Then we have n equals 2, n equals 3. Big thing here is to remember that when we hit the n equals 3, we have 3s, 3p, we also have 3d, but that 3d shows up down here a row below. So that's going to show up after the 4s and before the 4p. So remember that. Now, when we look at n equals 1, L is 0. So we only have 1 orbital. All right? That makes sense. We know that the s has 1 orbital. Look at our n equals 3. Okay, we can have s, p, and d subshells. So we can have multiple subshells in there. Let's keep going and let's talk more about the shells and the subshells. So when we look at the shells, that's easy to say, shells and subshells, as our n is increasing, as we go up by row, we've got our increasing shell number. Then we know that we've got our S block, D block, P block, and F block. How much do we really have to worry about the F block on the MCAT? Kyle's wondering. He wants to know. How much do we really need to know? Not a lot. Not a lot. Those are the funky ones. Those are those weird actinide, lanthanide series that really the only people that use them were people like Madame Curie, people that make them in a lab. So we really don't need to know much about them. Yeah, some weird inorganic chemists that want to make them in their lab. Remember, a lot of these don't occur naturally. Okay, so very, very few people actually look at them. Let's talk about our spec notation. What this does is our spectroscopic notation is telling us in shorthand where electrons exist in something in particular. Let's talk about titanium here. I want you guys to look at that and tell me, what is our spectroscopic notation when we're looking at this? I see lots of us typing. That makes me very happy. That means you're getting this really, really quickly. Very, very nice. I see lots of us typing in there. Ah, you guys went straight for the shorthand. Nice. The longhand would be 1s, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Now, I love how you guys went backwards, came up here to the noble gas that's right in front of it and said, no, no, no. We're going to go even more shorthand, and we're going to say argon plus our 4s2 and our 3d2. Now, what happens if I want to remove 2 electrons from this and make this a positive cation? Where am I going to lose those electrons? What is this going to be? Take from the highest energy level first. So now give me my argon, and then what's left over? Kelsey, you've got it. The 4s2 will be lost. 4s2, it's going to be argon and then 3d2. Why? Because 4s is in a higher energy level. Therefore, those guys are not as close to the nucleus. They're going to go away faster. So, David, think of it as because the N is higher, okay, 4 versus 3. They're a little bit farther out. Remember, it goes 1, 2, 3, 4. Because they're farther out, they're at a higher energy level. They can go away more easily. Okay, that's the easiest way to think of it. Let's practice with another one. So boron here. When we look at boron, we have helium plus 2s2 and 2p1. How about Ga down here? That's a weird one. We don't use that very often. Give me that one. Go ahead and start with your argon. Let's do the shorthand as short as we can make this puppy. So we're adding these guys in. I love it. Everyone's typing. We've got argon, and then we have a couple of things. 4s2, 3d10, 4p1. Nice. Ashley, William, Brandon, you guys got this. You are all over how we do this. All right, now let's switch and look at the magnetic quantum number. This is giving us our orbital. You guys were so excited to get to that orbital. Here we are. So this is our third quantum number here. When we look at this, it's the possible values, and it's our negative azimuthal number to our positive azimuthal number. Well, if we have S has an azimuthal number of 0. So that's just going to be 0, which means it only has one orbital. This is not shocking to us. We know that it has one orbital. Our P's, however, go from -1 to +1 because the azimuthal number is 1. So we have -1, 0, and 1, which tells us there are 3 subshells. Now, Px, Py, Pz. Do we, for test A, actually have to know the shapes of our orbitals? No, we don't. Okay, really quickly, tell me, how many orbitals are in the D subshell? 5, good. And how many in that funky F that we never really have to deal with? 7, good. Now, if we're talking, since we use the p orbitals more often, if we're talking about the p orbitals, does it matter which order they fill? Does it have to fill px, then py, then pz? Good, Brandon, absolutely not. For convention, because we think linearly, we think logically, we always do it px, py, pz, but in reality, it really doesn't matter. This leads us to our final quantum number, which is the magnetic spin, and tells us if this is going up or down. So 1/2 or -1/2. And this tells us the spin. They can either spin up or they can spin down. Again, here, it really doesn't matter if we fill the ups first or the downs first. For convention, we fill the ups first. But these guys just don't care if it fills the ups or the downs first. So these are our 4 quantum numbers. Make sure you know what they are. Okay, so we go from shell to subshell to orbital, then within that orbital, exactly how are our electrons spinning. All right, with that said, you guys are ready to do some questions. We're actually going to have you do these questions on your own. So we'll do one at a time and then go over them. We're actually going to give you 45 seconds. So Kyle, can you set me a timer for 45 seconds? And then we'll go over this, and we'll look at the 2 possible ways that we can approach this question. So 45 seconds. Good luck. We'll see you guys in 45. All right, notice that I have pulled a poll pod up. I will leave this poll pod up for the sets of questions as we go through the question. And I can tell you, I won't show you the poll pod, but I'll tell you that 100% of us got this correct. There are two different ways to do this. Does everyone remember the Christmas tree way? Does everyone remember seeing that in different places? All right, so there are two ways to do this. Whoops. Can one of you guys get the poll back up for me? Sorry about that. The two ways to do this is to draw our little Christmas tree. Am I going to take the time to draw that Christmas tree and say 1S, 2S? Oh, goodness, no. It is absolutely not worth it. So what is the other rule that I can use? Well, that's going to be the N plus L rule. That makes sense. N is our number, L is our subshell. So remember, S is 0, P is 1, D is 2, and F is 3. When we go through and we do that, notice what we have. Notice that we have a tie. So whichever is the lowest energy will fill first. In our tie here, everyone picked 3D. Why did you pick 3D over 5S? It is the lower energy level. The lowest shell will absolutely fill first. Love it. Perfect. You guys got it. All right. Let's try another question. I want to see another 100% on here. This was really impressive. So we're going to give you another 45 seconds. If I glance at the answer choices, what do you notice really quickly about the answer choices while our timer is getting set up? What do you notice about that? Oh, they're principles. They're rules. Yes, I have to know these definitions. Yes, I have to know what they are for test day. So let's go through these. And since some of you are already answering, we should see something perfect. See you guys in 45 seconds. All right. I will tell you that 65% of us got this correct. So when we're looking at this, which of the following rules states that no two electrons can have the same four quantum numbers? Makes sense. If they have the same four quantum numbers, they're right on top of each other. We know that this is not going to work. So let's talk about each of these rules. Hund's rule, what does Hund's rule tell us? This is kind of the way that we fill movie theater seats. What does Hund's rule tell us? How do we fill theater seats? I don't know about you guys. They pair individually before pairing. They want to be far from each other, so they're going to go into the PX, the PY, the PZ. Okay, you never walk into a movie theater and go to an open seat that's right next to somebody else and just sit in it. We always leave a seat in between us. So that's exactly what Hund's rule says. All right, what is the Aufbau principle? Ah, yes, nice, Ashley. Very, very quickly done. This tells us that electrons fill those lower energy subshells first. Pauli's exclusion principle, I'm going to move this over to the left now. Pauli's exclusion principle is the one that absolutely tells us that we can't have four exactly the same quantum numbers, or we've got two guys right on top of each other. And then nobody picked octet rule, which is fine and perfect, because the octet rule just says we want to have 8 valence electrons. We want to fill that octet. Very, very well done. We've got one more question, so we're going to set the timer again for 45 seconds, and we're going to have you guys do question number 3. You were nailing this earlier, so I know that you can get this right. We're going to reopen the poll, 45 seconds. Good luck. All righty. So I will tell you that about 25% of us got this question correct. So my first question to you is, what is the iron? What is an iron neutral ion? What is that going to be? So we have to start there. And we're going to look at our periodic table to get it. Ah, argon, 4s2, 3d6. Nice, Hannah. Okay. What does it mean to be a free iron 3 ion? What does that mean when they say iron 3? Ah, iron 3 plus. Okay, iron can be 2 plus, iron can be 3 plus. So I'm going to take away 3 of my electrons. The first 2 are going to come out of the 4s2. The third one is going to come out of the D. And so that's going to leave us with answer choice A. Now, this explains to us why we typically see these as iron 3 plus. Can we be iron 2 plus? Sure. If we're iron 2 plus, we're argon 3d6. What is the difference in stability between iron 2 plus and iron 3 plus? I have a 3d6 and a 3d5. Which one's more stable? Which one of those is more stable? Actually, the iron 3 is more stable. The iron 3 is more stable because I have 3d5. I have a half-filled orbital. Remember, if I'm an atom, I'm very, very stable with half-filled or fully filled orbitals. Paramagnetic, yes. So, if I have a 3d6, which is iron 2 plus, it's not as stable because I have just one beyond that half-filled orbital. So it's going to really want to kick off the other one. So this is why we see iron 3 plus more often than we see iron 2 plus. Okay, these are the little things that we need to understand for test day so that we've got those points that we so well deserve. Now, with that said, we're going to move to our next session. And this next section is talking about the periodic trends. So we really need to be able to understand our periodic table. Now, our periods, these are going across. These are our rows. Our families or groups are our columns. And when we're looking at how things react, do we look at their reactivity in periods or do we look at their reactivity in groups? Groups, absolutely. Absolutely. So there are some other groups that we need to know, and we'll talk about the groups in a minute. But the one thing that I want to pull out here is when we're looking at our periodic table, what is this number right here represent? So we're using carbon as an example. What does that represent? The atomic number, the number of protons. Nice. So what does 12 represent then? The atomic mass, the protons plus the neutrons. Perfect. So a couple of things we can get off of here, our atomic number and our atomic mass. We can also get the valence electrons. How many valence electrons does carbon have? Let's just stay with carbon here for a second. Yes, it has 4. It has 6 total electrons, Ashley, but only 4 in the valence shell, which is our 2s2 and our 2p2. And then the final thing that we have is our electron configuration. We've already practiced with this. This is going to be helium, 2s2, 2p2. You absolutely know how to do that one. So let's move on and talk about periodic trends. This is important. What happens as we move up or as we move to the right on the periodic table? All of these have to do with the effective nuclear charge. So what the effective nuclear charge is how much pull do I feel from the nucleus? So how positive is that nucleus? If I look here, these two are going to be pulled toward the center. As I get another shell, yeah, these guys are going to be pulled toward the center too. But they're also going to be pushed away. And they're going to be pushed away by the electrons in that inner shell. Shielding, nice. As I continue to go out, these guys will be pulled toward the center. However, they will be pushed out by both sets of electrons that are underneath them. Now, when we look at this, this really does have to do with the periodic table. When we look at this, we're going to have, as protons increase from left to right and bottom to top, our effective nuclear charge increases. So here's how I want to look at this. We're going to use sodium and fluorine as examples. Okay, sodium, when we look at that, if you look at sodium, which is right here, if we look at our sodium, sodium has 11 total electrons. From that, I'm going to subtract the nonvalence. Well, 10 of those are nonvalence. So sodium has a +1 charge in its nucleus. This is not talking about losing an electron. This is just saying its effective nuclear charge is +1, as is everything else in the row. If we look at fluorine up at the top, fluorine has 9 total electrons. Only 2 of those are going to be nonvalence. So fluorine right here has a +7 charge. Am I going to be more attracted, if I am an electron, to a +1 charge or to a +7 charge? Ah, the +7. This explains why it increases from left to right. Now, we're going to continue to use francium and fluorine. These are what we're going to use for our examples here. So our +1 charge also on francium, which again explains why it goes from bottom to top. Now, all of our periodic trends except for one follow the effective nuclear charge, how much pull I feel from the nucleus. And the one that does not follow, you guys are already a step ahead of me, is our atomic radius. If I am feeling pull, a lot of pull, I'm going to get closer to the nucleus. So this is an example of our radius. So as we get larger shells, we get a larger radius. So here, if our effective nuclear charge increases from left to right and bottom to top, the atomic radius is going to do the exact opposite. And this is because there are, whoops, sorry about that, really clicked, that really did something weird. Sorry about that. So this means that if I'm looking at francium, it's going to have a nice, big, fluffy. Whereas if I look at fluorine, fluorine, because it's +7, it's going to be pulled really, really close. This is the only one that goes opposite of our effective nuclear charge. All right, let's talk about the next two. The next two are ionization energy and electron affinity. Ionization energy is the energy required to remove an electron. Now, just looking at the periodic table, we know that sodium, things like that, are going to have +1 charges. Fluorine, chlorine, they typically, if they're ions, have a -1 charge. So I can easily remove something, an electron, from my group 1 and my group 2. Not a problem at all. You look at sodium, you say, I want an electron. It says, give me 400 joules of energy. I'll give it to you. If you look at fluorine and say, fluorine, I would like one of your electrons. Fluorine's going to go, I need 5,000 kilojoules of energy. I need a small nuclear device. I'm not giving it to you. So this follows the effective nuclear charge. Increases bottom to top, left to right. Our electron affinity is the energy that is released when we actually get an electron. I'm going to use an example here from YouTube. I know you guys have all seen some sort of video like this. If a kid on Christmas gets the one present he's been asking for months, and he opens it up, what does he do? You guys have all seen the YouTube videos of kids doing this. They scream, they go crazy, they jump around, they let out a lot of energy. This is my fluorine. Okay, fluorine is going to be so excited to get that one electron to fill its octet. Group 1, however, sodium, francium, they're that other side of that. We all know this person. And this person is going to be the one that you give them a present and they look at you and they go, oh, I just got rid of an electron. Do you have a receipt for this? Does everybody know that person? Or maybe is that person? Hannah is that person. Okay, that's our group 1. That's our francium. That's our sodium. They're like, ugh, we don't like that. So they're going to have a very, very low electron affinity because they don't want an electron. So this is going to follow exactly our effective nuclear charge. Our final periodic trend that we're used to talking about is electronegativity. What is my most electronegative element? Okay, Paul wants to know, what is it? Oh yes, it is absolutely fluorine. And this is because it has a lot of attraction in a bond. This is going to increase just like effective nuclear charge, bottom to top, left to right. Now, if we look at other things besides fluorine, if we look at carbon and oxygen here, oxygen has more electronegativity, so it's going to pull the electron density toward it, giving me a dipole. And in this case, we have that wonderful dipole. So this increases left to right, bottom to top, just like our effective nuclear charge. All of them follow the effective nuclear charge except for atomic radius. Let's talk about the exceptions to these guys. The exceptions to these guys are our noble gases. Okay, tell me something about the noble gases. What do we know about noble gases? What makes them happy? Oh, they're snooty. I love that, Hannah. They're content. They're stable. Okay, they have a full octet. So let's talk about what they do. So when we look at these typical trends, they do follow the atomic radius trend. Okay, as we go from helium down to xenon, it's getting larger. They also follow the high ionization energy. They have a full octet. Are they going to give you an electron? No way. They're going to give it to you less than fluorine is going to give it to you. So that's absolutely true. There are two things, however, that break the trend. And these two are their electron affinity. Okay, even though they're on the right side, they don't have a good electron affinity. They have a full octet. They're happy, they're done. And then the other one that they don't follow is the electronegativity. So both of these go against the trends. Realize that they're just a little bit different. Okay, so keep that in mind. Now, let's talk about our half-filled and fully filled. Let's go back to our iron 3. Why is iron 3 more stable than iron 2? It's half-filled. So half-filled and fully filled subshells are exceptionally stable. Now, what we're going to do here is we're just looking at the expected trend of ionization energy. Okay? We expect that lithium has a low ionization energy. It likes to be positive. It's going to give you a proton. We expect that neon's going to have a very high ionization energy. It's going to go, not a chance am I giving you an electron. But I want you to look at what's real. So the one on the left was what we expect. This is what we actually have. So notice that some of these are outside the realm of what we expect. Beryllium has a fully filled 2s orbital subshell. It's happy. Nitrogen has a half-filled or p orbital. It's happy. So it's got a higher ionization energy because if I'm fully filled or half-filled, I don't want to give up an electron. I want to be as stable as possible. So the more stable that I am, the higher my ionization energy. So this is what it really looks like. It doesn't follow a nice linear path. Okay, and this makes sense when we think about it. So our fully filled and our half filled have higher ionization energies because they're happy. Now, let's talk about some more exceptions to our trends, and these are our ions. When we look at our ions, if we look at the metals, these are typically going to be cations. They're typically going to lose electrons so that they can be positive. And remember our d orbitals, okay, our d subshell. These guys are our transition metals. They're very, very easy to go back and forth between multiple oxidation states, between losing electrons. So these guys are typically positive, cations. If we look over here on the right, these are typically anions. For instance, oxygen we know is always going to be -2. Fluorine is going to be -1. And then we've got our guys on the right, our noble gases, that are just not going to be charged. So let's look at what we have here as far as our radius. Okay, argon has got a radius that is just a little bit different. If we look at these three, calcium has a smaller radius. The reason calcium has a smaller radius is because it has more protons. It's going to pull those toward it. But here we're looking at just the size of the regular atom. What if I make it an ion? Okay, if I look at chlorine minus, argon, and calcium plus, these all have the same exact electronic configuration. They all have the same exact number of electrons. However, which one has the biggest radius? Which one's the fluffiest here? Anions are the largest. Yeah, that's going to be calcium. Or, sorry, not calcium, chlorine. Anions are the largest. Our cations are going to be the smallest. Why? Because notice that calcium has 2 more protons than argon. It has 3 more protons than chlorine. So if I have the same number of electrons, they're going to look at that calcium and they're going to say, you have more protons. I'm getting closer to the middle. Yeah, greater pulling power. That's a great way to put it. It's a great way to put it. Okay. It's time for you to do some more questions. I'm going to do the same thing we did earlier. We're going to set a timer for, I think you guys can do these. You're doing really well in 30 seconds. Okay. So let's go ahead and give you 30 seconds, and then we'll go through this one. This ranking, I'm going to tell you something important. Look at least to greatest. When you see that on test day, make sure you know that this is the least, this is the greatest. Make sure that you know that. All right, 30 seconds. We'll see you in 30. All right, I will tell you 79% of us got this correct. So here's what we're looking at. I'm going to pull that off the board. And what's the trend in electronegativity? We know that it increases left to right, bottom to top. So if it increases up and to the right, let's look at carbon and nitrogen for just a minute. Which one is going to be more electronegative? Which one will be more electronegative? Oh, yes, nitrogen is more electronegative. So 2 should be greater than 1. Notice when, or what, 2 should be greater than 1. So what does that eliminate? Well, that eliminates A. That eliminates B. Love it. Now let's look at sodium and potassium. If it increases as we go up, sodium is going to be more electronegative than potassium. So that means that 4 has to be greater than 3. Notice that eliminates D. I'm done. I'm left with answer choice C. All right, you guys are doing really, really well on this. So what we're going to do is leave you 5 and 6 as homework. These will be in the recaps that you get after. We want to have you do these as homework for the following reason. You guys are doing really well, number 1. Number 2, there is value in doing what we have talked about in class and doing those on your own. So you're still going to have the answer choices and what they are, but we really want you to do those on your own so that you can practice that same thought process. All right, this gives us to our third learning goal. And our third learning goal is to really look at where electrons are. Are they being shared? How are they being shared? So as we look at this, we know that when we look at Lewis dot structures, oxygen has 6 valence electrons, which means it needs 2 bonds to have a full octet. Hydrogen is one of those guys that breaks the octet rule. It has 1 valence electron. It only needs 1 more to fill that first shell. So when we fill them with the Lewis dot structures, we pair them up, make bonds, and here we realize that we do have electronegativity, giving us a dipole. And we know that, and that gives us a vector sum. We all know water is a dipolar ion. Now, let's talk about intramolecular bonding. What does intra mean? Well, it means within. So this is inside of a particular molecule. And what we're going to be talking about here is the Pauling scale for electronegativity. It goes from 0 to 4, 4 being the most electronegative. Okay, that would be our fluorine. Now, as we go through this, let's talk about our different bonds. An ionic bond is the strongest of our electrostatic attractions. This is not a real bond. This is not like a covalent bond. Okay, this is actually an electrostatic attraction. What happens is that chlorine is so electronegative, it actually steals an electron from the calcium. And then the calcium just kind of follows it around because it took its electron. So here, our difference is greater than 2. Okay, so this is why it's an electrostatic. These are fully charged ions. Calcium gives up 2 of its electrons. Each chlorine grabs 1 and says, we're good to go. Now, when we look at this, electrostatic attraction, positive versus negative, Michelle, positive versus negative. When we look at these, they actually show up as these cool lattice works. So this is what your table salt looks like. Okay, it's got these really cool lattice works. Now, a covalent bond is an actual bond. This is where we're sharing the electrons. We say, you can't have it completely. We're just going to share it. And a polar covalent bond is our water. So electronegativity difference has to be somewhere between 0.5 and 2. If it's greater than 2, we actually steal an electron. So here we've got partially charged atoms. We know our oxygen is partially negative charged. So we have that weak electrostatic attraction because we're sharing. Okay, hydrogen and oxygen are sharing that electron. Because we're sharing, there's an actual bond there, but this is polar because the oxygen shares it more often. It steals it more often. Okay? Now, continuing on with that, we've got our coordinate covalent. Coordinate covalent is where I have full octet. Okay, I have a full complement of electrons on my oxygen, but it's got some extra electrons, some lone pairs. So what it does is it goes to that positive hydrogen, which has no electrons, and it says, you know what, I'm going to share my electrons with you. So we make this new bond, and then our oxygen is positive. So both electrons in that bond come from one species, comes from the oxygen. And we all know oxygen doesn't like to be positive, so it's not going to hang out like this for very long. The next one is our covalent bond. And if the electronegativities are very, very low, there's a really close sharing of electrons, like carbon and hydrogen. So we get neutral atoms. There's negligible electrostatic attraction. There's one other covalent bond that's not on here that's called pure covalent, where they have the exact same electronegativities. This means F2, H2. So 2 different things that are exactly the same coming together. So when we look at this, our electronic or intermolecular strength is ionic is the greatest, covalent is the least. Now, this is inside a molecule. Intermolecular means between molecules. Here's how you can remember this. International flights go between countries. Okay, so this is between countries, not within a country. Now, when we look at our water here, we know that we have bond dipoles. We have a molecular dipole here. So these guys can have these electrostatic attractions, the positive and the negative that we were talking about earlier. Here, they just come together and they make this nice big grouping because of these electrostatic attractions. What is our strongest intermolecular force? Hydrogen bonding is actually number 2. Hydrogen bonding is actually number 2. Number 1 is our ion dipole. So if I have something like sodium chloride or calcium chloride in a polar solvent like water, it's going to yank those 2 ions apart, and then it's going to go around them. Okay, so our strongest is actually our ion dipole. This is what causes solvation. This is important later in general chemistry. This is very, very strong electrostatic attractions. Then we get to our hydrogen bonding. Hydrogen bonding is actually number 2. For hydrogen bonding to occur, we have to have nitrogen, oxygen, or fluorine that our hydrogen is attracted to. Now, that's our second. Our third would be dipole-dipole. This is where we have polar bonds, so we end up with a molecular dipole. This requires a molecular dipole, and its opposite ends associate. The next would be dipole-induced dipole, which we're not going to talk about. Instead, we're going to talk about dispersion forces. Be careful with calling it van der Waals. Van der Waals is actually dipole-dipole, induced dipole, and dispersion. So a dispersion is just present in all molecules. We have this nice cloud around us. All right. For the questions, we're going to give you those as homework. Okay, you understand what we're looking for intermolecular forces. When you're looking at boiling points, you really want to look at the higher boiling points being hydrogen bonding and size. Our next one is going to be looking at hybridization and shapes, so bond geometry. sp3 hybridization. What happens here is, let's look at carbon. Carbon has 2s and 2p electrons. So what happens is one of the s's actually leaves and becomes 3p electrons. So we have 2 half-filled orbitals. And here, this is lower energy. So we call this sp3 because one of the s's left and went to the p orbitals. So this is an sp3. When we look at this, notice all of these have 4 different molecules bound to them. When we look at this, this is called tetrahedral geometry. It's 109.5 degrees. Do you need to know the exact numbers? No, the MCAT will not ask you that. But you do need to know that 109.5 is the optimal, what we really, really want. So other sp3 hybrids here, we've got carbon tetrachloride, we've got our carbanions, we've got ammonia, and we have water. So all of these with the extra electrons, those electrons are considered to be sp3 hybridized, and this is considered a tetrahedral electronic geometry. sp2 hybridization is where we have a pi bond. So this, when we look at it, we've got that pi bond. Double, triple bond is going to be a pi bond. So both of our carbons in here are sp2 hybridized. When we look at this, this is 120 degrees. This is larger than what we want. And this is a trigonal planar. Okay, you can see that triangle in there, which is why we call it trigonal. And you can see that it is planar right here. Other sp2s that we see quite often are different types of aldehydes or ketones. Now, when we look at the methanium, that one is one that's not quite as stable, okay? The methylene is definitely not stable when we look at that. Carbon does not like to have negative charges. Now, our sp hybridization is 2 pi bonds. So when we look at this, this is linear. This is 180 degrees. So it's got that nice linear geometry that we have here. Other sp hybrids that we see are going to be things like propydiene. Notice that it's linear across those carbon bonds. Cyanide, our hydrogen cyanide. This is an acid. That is linear across that cyanide. We also see carbon dioxide, another common linear one that we have. Now, our sp3d and our sp3d2, these are not hybridizations that they expect you to understand on test day. What they expect you to understand is that this is phosphorus. It expands its octet. It's called trigonal bipyramidal. Sulfur is going to be an sp3d2. Again, you're not going to be asked for this one, but we can expand our octet. This is called octahedral. Okay, so this is an octahedral. Now, we mentioned that our ideal bond angle is 109.5. Okay, these all are going to have electronic geometries that are tetrahedral. However, the nitrogen, those lone electrons, they take those arms and they push them down. So if they're pushing them down, this should be a bond angle that is smaller than 109.5. It's actually 107. If I have 2 lone electron pairs, like I do in water, what does that further do to my bond angle? I now have 2 lone electron pairs. Oh, it's bent. It decreases it. It pushes it down even more. Okay, we're repulsing there. So this one is going to be 104.5. Now, is the MCAT going to ask you for our 107 and our 104.5, those exact numbers? No. They expect you to know that because of the lone pairs of electrons, they are smaller. That's all they want to do. Definitely understand the 109.5 is the optimal bond angle. That you definitely need to do. All right. So, electronic versus molecular geometry. Electronic geometry looks at where all of the electrons are. So, we already mentioned methane, ammonia, and water. If we look at all of those and look at the electron pairs, the electronic geometry is all tetrahedral, which is our 109.5. Okay, so these are all happy. However, the molecular geometry, looking at the bond angles, not 109.5, right? So when we look at the actual bond angles with the molecular geometry, methane still tetrahedral. Ammonia, trigonal pyramidal. Look at that shape, 107. And then water, we know is bent, is really small. That's 104.5. So understand the difference between electronic geometry, okay, our electrons, and our non-electronic geometry, which is our molecular geometry. Okay? So for this, I would like to look at just question 11. And then after question 11, we will be done. So the others you're going to do is homework. So rank the following from least to greatest bond angle. So least is going to be over here on the left, and greatest is going to be over here on the right. What is my biggest bond angle between all of these? Which one's linear? It's 180. It's going to be carbon dioxide. So I'm going to get rid of everything that doesn't have carbon dioxide as the largest, and water is the smallest. So then I have to look at my trigonal planar, and my carbon tetrachloride I always know is tetrahedral. It's 109.5. So which of these is larger? My BO3, my BOH3, or my carbon tetrachloride? Notice we only have to do the middle two. Yeah, my BOH3. Okay. So notice that once I have the largest and smallest, all I care about are these middle two and ranking those. Anytime you have carbon with four things around it, it's always going to be tetrahedral. So it's always going to be 109.5. All right, so what we did is we looked at and figured out our periodic trends. After our periodic trends, we looked at intramolecular and intermolecular bonds. And then we ended up with our bond geometries. And you've got those on the end so that you have these. Thank you so much for joining us for electrons. This is where all the fun happens. Once we know what our electrons are doing, we can have lots and lots of fun. You are very, very welcome. We will see you in another session. Have a great night.